In the reaction between potassium hydroxide and nickel sulfate, nickel hydroxide is going to precipitate out, and potassium sulfate is also on the product side. I've written the balanced equation and done the housekeeping, and the next step is going to be to determine the limiting reactant. And the way that we do that is to determine the number of moles of each reactant. So we're starting with 0.100 liters. We'll multiply that by 0.2 molar KOH, and that's going to give us 0.02 moles of KOH. And I'll do the same thing for the nickel sulfate. I have 0.200 liters. Multiplying that by a molarity of 0.15 molar gives us 0.03 moles of the nickel sulfate. Next, I'm going to divide each of those by the coefficient in the balanced equation, and the potassium hydroxide has a coefficient of 2. So that's going to give us a product of 0.01. I'm not attaching any sort of units to that because this is just the shortcut method of determining limiting reactant. And the presumed coefficient in front of the nickel sulfate is a 1, which gives me a product of 0.03. Whichever one gives you the smaller number is going to be your limiting reactant. So my potassium hydroxide is going to be my limiting reactant, and that's what I'm going to use to determine grams of nickel hydroxide. So we'll go back to those moles available of potassium hydroxide. We'll do our mole to mole ratio. In the balanced equation, we have 2 moles of the KOH to 1 mole of the nickel hydroxide and 1 mole of nickel hydroxide has a molar mass of 92.5. The last part of this problem asks us to find the concentration of each ion that remains in solution. So what I'm going to do is I'm going to write the equation like a net ionic equation. So when we write a net ionic equation, we get rid of all of the ions that don't actually take place in the reaction, and those are the spectator ions. So in this instance, potassium would be considered a spectator ion. The hydroxide, of course, goes into forming the precipitate, as does the nickel. But the sulfate ion is also a spectator. So remember, the spectators are just sitting there in solution doing nothing. They don't actually take place in the reaction, and the reaction here is the hydroxide and the nickel forming the precipitate. So whatever we started out with in terms of potassium ions is still sitting there in the solution. It didn't react. Same thing with the sulfate. Whatever we started out with is just sitting there in the solution. It didn't take place in the reaction. So since we started out with 0.02 moles of potassium ions, I'm going to find the molarity, the concentration of those ions in the solution by taking moles of potassium ions and dividing that by the volume of the solution. Now back to the original problem, we had 0.1 liters of the KOH, and we had 0.2 liters of the nickel sulfate. So our total volume then is going to be 0.3 liters. So that's going to give us a concentration of 0.0667 molar in terms of the potassium ions. And we began with 0.03 moles of the sulfate ions, and dividing that by our total volume will give us a molarity of 0.1 molar of the sulfate ions. So that leaves us concentrations of our nickel and our hydroxide. And I just did that backwards. Now, we know that the potassium hydroxide we calculated to be our limiting reactant, which means it gets completely consumed. But we also know that potassium is a spectator ion. So in reality, it's really not being consumed. What is being consumed is the hydroxide ion from that compound. So what's left? Nothing. The hydroxide is really the species that gets completely consumed. Okay, so hydroxide ions, gone. So the only thing left for us to figure out then is what is the concentration of the nickel ions. Now getting rid of those spectators and writing this as an actual net ionic equation, let's go back to what we originally started with. In terms of moles of nickel, I began with 0.03 moles. And in terms of the hydroxide ions, I began with 0.02 moles. Okay, and we know that this gets completely consumed. The question is, how much of this did it bind up with to make our nickel hydroxide? So if I started with 0.02 moles of hydroxide ions, and I know I need 2 moles of hydroxide ions for every 1 mole of nickel ions, I'm going to use 0.01 moles of nickel ions. Okay, so if I started with 0.03 moles, I'm actually using 0.01. That's going to leave me 0.02 moles of nickel ions in excess. And they ask us for that in terms of concentration, which means molarity. So I'm going to divide that by my volume, which again, starting with 100 milliliters of one, 200 milliliters of the other, 300 milliliters total, we have a volume of 0.3 liters. Will give us a molarity of 0.067 molarity with respect to the nickel ions.